All right, guys, let's try to make our way through this 2016 and 2015 free response. Okay, so the first question, you've got this set up. There's a cart of mass m, a force sensor is attached to the cart. A motion sensor is used to measure the acceleration of the cart with the positive direction to the right. On the dot below, which represents the cart, draw and label the forces that act on the cart. Each force must be represented by a distinct arrow starting and pointing away from the dot. Okay, so first of all, it's easy to forget this, but you got to have the normal force and the force of gravity, and those need to be equal. You know, you don't have to get out a like measuring stick or measuring tape or a ruler. That's the word I was looking for to do this, but they do need to be pretty close to equal. The other thing is that it is being accelerated. It says it's being accelerated. So since it's being accelerated, the tension force, the force in the string, is got to be bigger than the friction force, which is going in the opposite direction. Okay, so there's our first bit. For the next part, a student pulls the force sensor with a constant force and accelerates, and the cart accelerates. This is repeated for several trials with a different constant force used for each trial. The data are recorded in the table below, and it gives us the data. Okay. Oh, sorry. By the way, on A, you got a point for labeling tension, friction, normal, and you got a point for for labeling tension. You got a point for labeling friction. You got 1 point for doing normal force and force of gravity, and the third point is you. No, those were the 3 points. Sorry. Now for the next bit, just graph this. I'm gonna let you look at the graph that I sent, or the problems that I sent out, the answers, and you can see how it's supposed to be graphed. I don't want to waste your time by graphing this, but you do get a point for using a correct scale, for plotting it correctly, and drawing a straight line with consistent data. So basically you get 1 point for drawing a best fit line, you get 1 point for plotting the data correctly, and you get 1 point for using a correct scale. In this case, they didn't give you points for labeling because they already labeled it. Anyway, for step 2, you're supposed to use the straight line from the chart to calculate the mass. Note that when you do this, you're not using the points that are on the data table. You're using points that are on the the line itself. So, like for example, if this is your line and these are your points. All right, I'm exaggerating this for effect, but if these are your points, then you could use this point and this point, but not any of those points that are off the line. All right, so if you do this, you should get, it depends on how you did it, but if you use slope formula, they're saying that it should be 2.16, and the unit here would be kilograms to the -1, because basically, remember a Newton, basically it's y over x, and then it's meters per second squared over a kilogram times a meter per second squared. And boom, it's 1 over a kilogram. All right, and then for part 3, you're going to use the straight line from the graph to determine the magnitude of the force of friction. Okay, this is a little bit tricky, but it's not terrible. So basically just add, or you plug it back into the formula. Tension minus the friction force equals mass times acceleration. You now have values for tension. I would use one that's on the line. If the force sensor reading, I'd use one that's on the line if you could. It looks like there's one that's on the line that's 0.55. 0.55 minus friction equals, you now have a mass. If you do, like, this is mass to the -1. So mass is going to be 1 over 2 to the 2.16, which is 0.463. Sorry, I forgot to finish that up. 0.463. And then, so you do 0.463 times A. You know A for that value. It looks like that value that I picked, that where the force reading was 0.55, the force reading would be the acceleration would be 0.6. So you could just make that 0.6 and solve for friction. If you solve for friction, it should give you a number around 0.272, depending on how you did this. Let's see what I gotten real quick. Maybe. So 0.463 times 0.6, and let's see, then 0.2722. Yeah, so I got the same thing that they got. All right, so part C, we are going to, the above experiment is repeated by using a constant force that's 0.45. The cart starts from rest at time t equals 0 and is pulled for a time of 2 seconds along the track. Determine the acceleration of the cart. So we now know the force of friction. So this is the friction force. So you can just do 0.45 minus 272 equals 0.46 times A, 0.463 if we're being technical, times A, and solve for A. A would be equal to 0.376 or 0.38 meters per second squared. And it says the string breaks at time equals 2 seconds. Calculate the time it takes for the cart to stop after the string breaks. Well, so let's figure out how fast it's going before the string breaks. So it was accelerating at 0.38 meters per second squared, v minus v naught over 2. So it's going 0.76 meters per second whenever the string breaks. So now the only acceleration, or the only force acting on it, is that 0.272. That's equal to 0.463A. 0.463. So it got an acceleration of 0.59 meters per second squared. And then you're just going to repeat this. So negative 0.59 equals 0 minus 0.76 over t. Solve for t. So 0.76 divided by 0.59 should be 1 point. Let's see. Make sure I don't lie to you. Yeah, 1.28. So t is equal to 1.28. Okay, you just solve that formula. All right, and then let's see. The experiment and analysis in parts A and B are repeated with the cart that has the same mass but a greater force of friction. Will the new slope of your line be greater than, less than, or equal to the slope in part B? And the answer is it should be equal to, because the mass is the same and the slope was basically mass over 1. So the slope, m, was equal to mass over 1, and since your mass is the same, you should have the same slope. And then the second question is, will the horizontal intercept of your new line be greater than, less than, or equal to? The answer is it should be greater than, because you're increasing that force of friction, and the force of friction was basically the intercept for that line. Okay? It was basically your starting force against you. All right, so moving on. All right, so we got the next question here. A block of mass 2m rests on a horizontal frictionless table and is attached to a relaxed spring. Basically, that means it's at rest and there's no tension in it. The spring has a nonlinear force. Ooh, yay. Got a nonlinear force. Okay, so that means whenever you see nonlinear force in a spring, it means that the spring force does not equal kx. It's going to be equal to this factor, negative bx cubed. Okay, so don't get confused here. It's not this. Where b is a positive constant and x is the displacement from equilibrium. A block of mass 3m with an initial speed v0 is moving to the left as shown. On the dots below, which represent blocks 2m and 3m, draw and label the forces, not components, that act on each block before they hit. So essentially, before they hit, there's no friction involved here. It says it's a frictionless table, so we've just got the normal force and the force of gravity. And I'm going to label this the normal force on force 1, and then the force of gravity, you could do just 2mg and then the normal force on object 2, and then 3 mg for that one. Okay. I suppose you could put FG1, FG2. I don't think there'd be anything wrong with that. Yeah, I can't see that there'd be anything wrong with that. And then for B, we're going to derive an expression for the speed of the block immediately after the collision. So immediately after the collision, it's just a conservation of momentum formula. So basically the momentum at point 1 has to equal the momentum at point 2, which means that 3m v naught has got to be equal to 5m v afterwards. And so if you solve for that, m's cancel. It's 3/5 v naught equals v. There you go. So that's B. C, determine an expression for the kinetic energy of the two-block system immediately after the collision. So you just plug it in again. Kinetic energy is equal to 1/2 mv squared. So kinetic energy is going to be equal to 1/2 times 5m times 3/5 v squared, which is a little bit hairy. But if you just kind of bring everything over and stuff, make everything work with the fractions, it ends up being 9/10 mv naught squared. Okay, you just multiply everything out, so it ends up being 15 on top and 10. What does it end up being? It ends up being 45 on top and 50 on bottom, and so you can. This should be squared. There we go. So it should be basically 9 times 5 over 25 times 2. So you end up getting 9/10. And then D, derive an expression for the maximum distance the spring is compressed. So a couple of things, what you want to do here is say that the spring's potential energy is going to be converted fully into kinetic energy. Okay? But we need an expression for the spring's potential energy, and the way we do that is basically a spring's potential energy is the integral of the force dx, and so we're going to integrate this from 0 to d, and we're going to do, negative bx cubed dx is equal to that k. So then we integrate that, we get negative b over 4 x to the 4th evaluated from 0 to d is equal to 9/10 mv naught squared. And then this ends up being, it's ugly. It is really ugly. All right, so this ends up being negative b d to the 4th over 4 equals 9/10 mv naught squared. Then you're going to multiply up by 4 and divide by b. So if I multiply up by 4 and divide by b, I end up with 36 over 10, which reduces to 18 over 5 mv naught squared, and then divided by, well, let's go ahead and just put the 5 on the bottom so it looks a little bit neater because it's ugly as is. 18 over 5b equals d to the 4th. So to get rid of that 4th, I've got to, I don't even know how to say that. It's not cube root, quad root it. I don't know. That's what the answer ends up being. Very, very pretty, I know. All right, so that's your answer. It'll compress this much. All right. For E, God bless, that's terrible. For E, in which direction is the net force, if any, on the block of mass 2m when the spring is at maximum compression? In which direction is the net force, if any, on the block when the spring is at maximum compression? So on block 2m, we're trying to figure out what force would be acting on it, and it would be to the right. I know this is off the screen now, but we've got it compressed. All right, so there's an actual distance d here that it's compressed from rest. So there is going to be, this is 3m, this is 2m. Whoops, sorry. Sorry. I'm trying to find the eraser. This is 2m. This is 3m, right? Yeah. So it should be right, and you get a point for like one for the correct answer and one for a reasonable justification. A reasonable justification is saying that when it's at maximum compression, it has a velocity of 0, but the horizontal force is still acting on the system, pushing it to the right. So basically, it's at the point where it stops pushing it stops applying. My bad. It's as long as it's on the left side of the 0 point, it's always pushing to the right, regardless of what the speed is. Okay. Number 2, there. Which of the following describes the magnitude of the net force on each of the 2 blocks when the spring is at maximum compression? The magnitude of the net force is greater on block 2m, and the magnitude of the net force is greater on block 3m, or the magnitude of the net force has the same non-zero value, or the magnitude of the net force on each block is 0. So let's see. So this is a little bit weird, but basically the instinct is to say that they have the same force because you got the same spring acting on them. But the deal is that since 3m is bigger and they're both going to be accelerating at the same rate, whatever it is, I don't know, let's say it's 5 meters per second squared. So they're both accelerating at the same rate. Since they're both accelerating at the same rate, because they're stuck together, the force on 3m has got to be greater than 2m because the mass is bigger. Okay, basically, F of 3m has got to be equal to 3ma, and F on 2m has got to be equal to 2ma. And so since the force has to be greater and they have the same acceleration, since the mass is greater and they have the same acceleration, the force has to be greater on 3m. And then finally, do the 2 blocks which remain stuck together and attached to the spring exhibit simple harmonic motion after the collision? It's a little bit beyond this class now because we, I think, are not doing simple harmonic motion, but the answer here is no. I mean, it will be moving back and forth, but the motion won't be harmonic because it is a non-linear force. Basically, since the force is equal to negative bx cubed, it's not going to result in harmonic motion. Only the force that is a linear relationship to distance will result in harmonic motion. All right, next up. This one seemed to give you all a lot of fun. So essentially derive an expression for the spring constant. Oops, sorry, I skipped a lot. Basically, you've got this thing here, and you've got it spinning around. When it's spinning at omega, the spring is stretched out to that distance that you see there. We've got the rotational inertia is given to us. The I's are given to us. As the motor begins to slowly rotate the platform counterclockwise as viewed from above, the platform reaches a constant angular speed omega. Under these conditions, the spring is stretched by an additional length of d over 2. Answer the following questions for the platform rotating at a constant angular speed omega. By the way, this is a horizontal platform, so looking at it from like a table. Derive an expression for the spring constant. So basically, the spring constant is going to be equal to the centripetal force on the spring because it's the only thing pulling this in since it's horizontal. And so the spring is going to be equal to m omega squared r. How do I know it's omega squared r? Because v is equal to omega r, and basically v squared over r is mv squared over r is equal to the force. So m omega squared r squared over r, boom, boom. There you go. So you're left with, that's the formula for the centripetal force. Then that's got to be equal to the spring force. So k, and the distance that it's stretched is d over 2. is equal to m omega squared r. And then you're going to plug in, sorry, forgot this part, plug in 2d for the radius. Now solve. So we're going to do k is equal to 4m omega squared. Yes, and you cancel out the d's. Okay, so there you go. There's your value for k. Now we're going to determine an expression for the rotational inertia of the block around the axis of the platform. If we're just doing the block around the axis of the platform, it should just be m r squared, which in this case is going to be equal to m times 2d squared, because it tells us right there the radius is 2d and it's at the edge, and so it should be just 4md squared. And then let's the rotational inertia for the entire system. So basically you just had to add them all up. So we're going to just do the I for the system is going to be equal to, though we just got there, so 4md squared. It's basically equal to the platform. It's going to be equal to the I of the block plus the I of the rod plus the I of the platform. And so we know what these values are because they give them to us. So I guess that should be the m of the block, d squared. They don't label it, so it's okay. Plus the I of the rod, which is m of the rod, d squared over 3. And then plus the m of the platform, r squared over 2. And so you just add all those up. Let's see. And it does give us the values for the mass of the rod and the mass of the platform. It's 3m and 5m, so we're going to put 3m in here for this, and 5m in here for this. And then when you add them all up, just using algebra, you end up getting it's equal to 15md squared. Okay? 15md squared. And then finally, we're going to determine an expression for the angular momentum of the entire system. So angular momentum is equal to I omega. So this should be equal to 15md squared omega. That's all you have to do there. All right, next up, for D, we are going to, so basically while this system continues to rotate, a small mechanism in the pivot moves the rod slowly until the center of the rod is positioned on the axis as shown in figure 3. The same constant angular momentum is maintained. Derive an expression for the distance x that the spring is stretched when the rod reaches the position shown above. Okay, so since you're bringing this in, and the centripetal force is equal to m omega squared r, since you're bringing that in, that means that, let's look at what happened. The k is going to stay the same, so what happens to the x distance? The x distance is going to get smaller because r is getting smaller, all right? And so basically, if we're going to derive an expression for x that the spring stretches now, we can do that by setting this up again, and in this case, instead of having r, we're going to have, because this distance was d over 2 as well, so basically the rod was a length d, and you brought half of it down, so now you got a length d over 2 above the pivot, got another length d over 2 here, plus x. So we end up getting x is equal to m omega squared d plus x. Oops, I forgot. Sorry about that. D plus x. There we go. And then now we're going to solve for x. The way we're going to do this is by plugging in what we found earlier for k, which was 4m omega squared. Notice that the m's cancel, the omega squareds cancel, so we're left with 4x equals d plus x. Whoops. D plus x. And if you solve for this, you get 3x equals d, or x is equal to d over 3. So there we go. We got an expression for x. For parts E, F, and G, assume that the center of the rod is still moving towards the axis of the platform. Is the entire system increasing? The angular momentum of the entire system increasing, decreasing, or remaining the same? The answer is it's decreasing. The reason it's decreasing is when you're bringing this in, you're lowering the system's I. The system's I is going down because the mass is getting closer to the center, but you're maintaining a constant omega, and so that means that when you do angular momentum equals I omega, if I is going down and W is staying constant, then angular momentum also has to go down. In order to keep the system rotating with a constant speed omega, is the motor doing positive, negative, or no work on the system? And the answer is it's got to be doing a negative amount of work on the system. Basically, you know it's doing negative work because if you're changing your momentum, then there has to be an impulse, an angular impulse. Means there has to be a angular impulse, and so basically, if there's an angular impulse, there's a torque being applied over a period. Torque being applied over a period of time. Which means that there has to be a force at a radius being applied over a period of time to change the momentum. If you have a force that's being applied over a period of time, it's also being applied over a radial distance. That means that it's going to be doing angular or linear work on the system. Basically, kinetic energy is decreasing, therefore you must have some work being done. All right, and then final thing is draw the like a force arrow, no, acceleration arrow. So we've still got the centripetal acceleration acting on this object, right? So the centripetal acceleration is still acting on it, so that's pulling down. But now, since there is that force that's like lowering there's something slowing it down, or not slowing it down, but basically causing it to lose kinetic energy. What should happen if you bring that stuff in, imagine, if you will, the skater pulling her arms in when she does a spin. When she pulls her arms in, she goes faster. If she was maintaining the same speed when she pulled her arms in, there has to be some force acting on her to slow her down. And so since there's a force acting on this to slow it down, there's got to be a tangential acceleration as well. And that means that there has to be a net acceleration that is down and to the right. Okay? All right. So that finishes up the 2016. So let's move on to 2015. So on this one, we've got a block of mass m being projected up from the bottom of the incline ramp with an initial velocity v0. The ramp has a negligible friction and makes an angle of theta with the horizontal. A motion sensor aimed down the ramp is mounted at the top of the incline so that the positive direction is down the ramp. The block starts a distance d from the sensor as shown above. The block slides partway up the ramp, stops before reaching the sensor, and then slides back down. All right, let me reread that to make sure I got it. So we've got negligible friction, so we don't have to worry about friction, which means the only force acting on it should be the force of gravity. The force of gravity, let's see, force of gravity sine theta should be the only force acting on it that's pulling it down the ramp. Block starts moving at a distance d. Okay, so we want to determine the acceleration of the box. So basically the force on the box is going to be equal to ma, which is going to be equal to mg sine theta. And it should be negative. Well, it's going to be going, which way do they define as positive? Positive direction is down the ramp. So since this is the positive direction, that means that's going to be positive acceleration. So A is equal to G sine theta. So there you go. That's acceleration. Number 2, determine an expression for the velocity of the block V. So basically V is equal to V naught plus G sine theta times T. I mean, I think that's all you got to do. V naught is negative, though, because it is going up the ramp, and we've defined down the ramp as positive. And then determine an expression for x of the block. The position is going to be equal to, remember, it's x naught plus v naught t plus 1/2 at squared. So x is going to be equal to d minus v naught t, because again it's not negative because the initial velocity is in the negative direction according to what they've set up, plus g sine theta t squared over 2. All right. Let's see. That gets us through that. So B, derive an expression for the minimum distance of the block when it's closest to the motion sensor. Express your answer in terms of m, d, v naught, and theta, and physical constants when appropriate. So basically what I'm going to do here is say that I'm going to go ahead and use the v squared equals v naught squared plus 2ad. All right. Now, let's see. First of all, notice that if I define this as d, it's going to be a negative number. Okay, so we're going to start there. So then we get this is going to be 0. And so I end up with 2. Well, since that's negative, I'm going to add it to the other side. So I get 2ad equals v naught squared. And so I'm going to go ahead and divide that. And I'm going to get d is equal to v naught squared over 2g sine theta. I'm just plugging in the number for acceleration. Now let's figure out what d is. So d should be, lowercase d should be capital D minus x min. So d should be capital D minus x min. And so let's see what that does. If I do d minus x min equals v naught squared over 2g sine theta, and then I bring the d over and the divide by the negative sign, I end up getting x min is equal to d minus v naught squared over 2g sine theta. Okay. C, we're going to derive an expression, sketch the graphs of x, v, and a as functions of time. So the acceleration should just be constant because it's just going to have that force of gravity acting on it the whole time. The velocity should start off negative and go to positive as it goes back down the ramp. And then finally, the position is going to start off positive and then come back up to positive, or sorry, start off, it's going to stay positive the whole time. This distance right here would be x min, whatever that would be. Okay, but basically because it's going to, since it goes to 0 and then comes back, we have to see a parabola, the full parabola on the x. That's what that is for. Okay, for D, we are going to, after the block slides back down and leaves the bottom of the ramp, it slides on a horizontal surface with a coefficient of friction mu k. Derive an expression for the distance the block slides without stopping. So after the block slides down and leaves the bottom of the ramp, it slides a horizontal distance. Okay, so basically we need an expression for friction first. Now friction is the only thing acting on it, so it should be equal to mass times acceleration. So mu times mass times g should be equal to mass times acceleration. So mu kg equals mass times acceleration. And I'm just going to plug that in now. So v squared equals v naught squared plus 2ad d. You'll notice I'm using this formula a lot because I don't have time in this thing. So the final velocity, if we're trying to figure out how long it slides before stopping, is 0. This time the velocity is positive initially because it's going forward, and so I end up with negative v naught squared on the other side, moving it to the side, equals negative 2 mu k g d. Now, you'll notice that I did make this negative, and the reason I made this negative here is because the friction force is slowing it down. So I'm going to divide, and I'm going to get v naught squared over 2 mu k g d. Dang it, d is equal to, man, I am not having a great day here. There we go, is equal to d. Boom. Okay, so the final thing you need to do is suppose the ramp now has friction. The block is projected up with a speed that's initial speed and comes back down the ramp. So the important bit here is that since there's friction, it's going to come to a stop well before the halfway point, and then once it comes to a stop, it's going to make its way back down slower. Now the reason for that is force of gravity and friction are working together. In this section, force of gravity and friction are working together to slow it down. And in this section, force of gravity and friction are going against each other, so the acceleration should be less. So in other words, the acceleration in the green is going to be equal to the force of gravity sine theta minus friction over m, and the acceleration in the red part is going to be equal to the force of gravity sine theta plus friction over m. They're going to be acting differently, okay? And so you should have a graph that looks something like that. Also, since it's going to slow down faster, that's the reason it stops before t of f divided by 2. All right, next up, we've got a lovely, looks like projectile problem mixed with a pendulum. Always love stuff like this. So we got a small dart of 0.02 kilograms is launched 30 degrees above the horizontal at 10 meters per second. At the moment it reaches its highest point in its path, it's moving horizontally. It collides and sticks to a wooden block, and that is suspended at the end of the string. The center of mass of the block is 1.2 meters below the pivot point on the string. The block and the dart then swing up until the string makes an angle theta. Air resistance is negligible. So to determine the speed of the dart just before it strikes the spring, basically that's going to be 10 cosine 30, because it's only the x component that we would be concerned with. So 10 cosine 30 would be 8.7 meters per second. So that's A. For part B, calculate the horizontal distance d between the launching point of the dart and a point on the floor below. Okay, so there's a couple things we can do here, but I'm going to do this. So basically, I'm going to do v naught y over 10 is equal to the time to the top. And since it's at its highest point there, that's what I can do. So I'm going to do 10 sine 30 over 10 is equal to t to the top. This is v naught y over 9.8. It's simply a reworking of the formula v equals v naught plus at, and you're just basically that goes to 0. V naught over a is equal to t. That's where that comes from. It's just a nice little thing to have on hand. So the time to the top is 0.5. If it's going 8.7 meters per second and it's in the air for 0.5 seconds, then the distance in the x direction is going to be equal to 4.35 meters. Calculate the speed of the block just after the dart strikes. Well, they stick together, so we're going to have momentum is conserved on C. So for C, we've got momentum 1 equals momentum 2, so 0.02 times 8.7 is equal to 0.12 V. And if you solve for that, let's see, 0.02 times 8.7 divided by 0.12 is 1.45 meters per second equals V. If you use 9.8 instead of 10, you're going to get slightly different answers here. Calculate the angle through which the dart and the block will rise before momentarily coming to rest. Okay, so for part D, we're going to do kinetic energy equals potential energy. And this is going to be equal to 1/2 times 0.12 times 1.45 squared equals mgh, and h is going to be, remember h is, in a pendulum, h is equal to L minus L cosine theta. It's just something to have on hand. And so you can solve for this. L 1 minus cosine theta, solve for L. You know M is going to be, you know these values, so I'm going to go ahead and plug these in. 0.5 times 0.12 times 1.45 squared is 0.126 equals 0.12 times 10 times 1.2, 1 minus cosine theta. We're going to solve for that in just a second. So minus 2 times 10 times 1.2 is negative 1.31, 1 minus cosine theta. Now we're going to solve for cosine theta. All right, give me a second. I think I've screwed up here, but I'm just going to redo it rather than try to go through that again. So D is going to be, I didn't screw up on the initial part. It's 1/2 mv squared plus mg, oh, no, not plus, equals mgl 1 minus cosine theta. Okay, so I got that part right. All right, let's do some canceling. So we got cancel the m's. We're left with 1/2 times v squared. Now v squared was, what was v squared? What was v? 1.45. So 1.45 squared equals 9.8 times 1.2, and then 1 minus cosine theta. Okay, now I'm going to do all right, 0.5 times 1.45 squared divided by 9.8 divided by 1.2. All right, that's better. So we got 0.089 equals 1 minus cosine theta. All right, I'm going to subtract 1 over, and then I'm going to take the negative sign off because we got the negative sign on the cosine as well. So we get 0.91 equals cosine theta. And then we're going to solve. There we go. And we get a 24-degree angle equals theta. Yay. Okay. I think I just typed this in wrong. It's this part was right. I just didn't want to go through it again. And then E, the block then continues to swing as a simple pendulum. Calculate the time between when the dart collides with the block and when the block first returns to its initial position. All right, so basically this is the period divided by 2. If you're looking at it, because basically there, back is the period. So if you're just going there and back, it's going to be period over 2. So the period of a pendulum is equal to 2 pi square root of L over G, and the period then would be equal to 2 pi square root of 1.2 over 9.8, which is going to be a number, 2 pi second square root 1.2 divided by 9.8, and then that's 2.2. Then I'm going to divide that by 2 to get the answer, so it should be 1.1 seconds. All right, and then for F, let's see. In a second experiment, a dart with more mass is launched at the same speed Would the angle that the dart makes increase, decrease, or remain the same? So it would increase because you're hitting it with more momentum, which means that you're transferring more momentum to it, which means it'll have a higher initial speed, which means that it should increase the angle. Basically, you're hitting it with more kinetic energy, so it should rise to a higher location. Let's see. Would the period of the oscillation after the collision increase, decrease, or remain the same? And it should stay the same. A more massive dart would only affect the, it's not going to affect the length of the pendulum, and the length of the pendulum is the only thing that can affect the period. As long as the angle stays under 30 degrees, it should be okay. Although I don't think technically you're required to know that. So basically you're just required to know that changing the angle of the pendulum won't really affect it. All right. There you go. All right, and last one. Yay, almost done. Okay, so using integral calculus, derive the rotational inertia to show that it's ml squared over 3. This has come up a couple times, so I probably want y'all to keep this one on hand. Basically, I is equal to the integral of r squared dm. And basically, what you have to do is show that basically you know that it's a uniform rod, so the density, the linear density, they're going to call that lambda, linear density. How do you spell density? There we go, density is lambda, and lambda is going to be equal to L over M. So if you're looking for a tiny sliver of the mass, the dm, it's going to be equal to lambda dx, okay? And so what that means then is that dm is equal to L over M dx, okay? And so, or not L over M, my bad. This whole thing, linear density should be mass divided by length, all right? And then that should be mass divided by length. That's my fault, all right? There we go. And so now, what you do is you take this dm and you plug it in here, and so I is going to be equal to the integral of r squared m over L dx. Whoops, putting too many equal signs in there. Dx, and you then are going to evaluate it from 0 to L, from 0 to the length here. And if you do that, I'm going to change r to x just to make this make more sense. So it's going to be x squared. Okay, so then we get I is equal to x cubed, mx cubed over L, evaluated from 0 to L. Sorry, I forgot how to integrate for a second. So mx cubed over 3L, evaluated from 0 to L. And notice this ends up being ml cubed over 3L. The L cancels, becomes a squared, and you're left with ml squared divided by 3. Okay, that's come up a few times, but this lambda equaling mass over length, and then dm equaling lambda dx, or dr as the case may be, it gives you the value that you're looking for. All right, derive an expression for the velocity of the free end of the rod at position B. Express your answer in terms of ml and any physical stuff that you feel you need to. Okay, so let's look at it. So basically, we've got potential energy is equal to rotational kinetic energy, because it's only rotating. It's not going to change its speed. So we got potential energy equals 1/2 I omega squared. And I'm going to change colors for this. So we end up with mgh equals 1/2 ml squared over 3 times omega squared. Now the reason I'm looking for omega is because if I want to find what the v is here, I need to do v is equal to omega r, and in order to do that I got to find omega. So I'm looking for omega. M's cancel, so we're left with how high is it to begin with? Oh, this is good. So the height is going to be this height of the center of mass, not the height overall. So the height of the center of mass is L over 2. So GL over 2 is equal to is equal to L squared omega squared over 6. And so we end up with, okay, so we've got this. So now what I'm going to do is I'm going to figure out what V is. So V is equal to omega R, which means that V over R is equal to omega. And R is going to be equal to L. So V over L is equal to omega. So I'm going to plug that in over here. So GL over 2 is equal to L squared. Actually, I'm going to go ahead and bring that 6 over. Let's go ahead and bring that 6 over. So that's equal to 3GL is equal to L squared times V squared over L squared, because I'm plugging this value in right there. And notice L squares cancel, and so square root of 3GL is equal to V. Yay! All right. Now, we're going to, oh God, now we're going to do a experiment. So we're going to do an experiment to test the validity. The student uses rods of various lengths that all have uniform mass distributions. That's important because it means their lambda's all the same, basically. The student releases each of the rods from the horizontal A position and uses photo gates to measure the velocity at the free end. The data are recorded below. All right, and so then we are going to indicate which quantities should be graphed to yield a straight line whose slope would be used to calculate a numerical value for G. And so if we use our formula that we just developed, which was V is equal to the square root of 3G over L, you could solve for this. V squared equals, V squared over 3L is equal to G. And so what you could do is you could put on your x-axis, so remember that slope is equal to y over x. On your x-axis, you could put the length, and on the y-axis, on the horizontal axis, you would put length, and on the vertical axis, you would put the velocity squared, and you would be able to get the slope. The slope would give you something that would resemble gravity. So you would need to make sure that if you do slope is equal to, if you do slope is equal to V squared over L, you just need to do 3 times the slope is equal to G. All right? No, my bad. 1/3 of the slope would be equal to G. And so use the remaining rows to label anything extra you would need. So you would just need to find V squareds. So just would have a second column for V squared. And then you would graph. If you look at the thing that they graph velocity versus length, versus the square root of length. That's fine as well. But I would do V squared over L. So meters squared, second squared. It doesn't really matter. You could do V squared versus square root of L, or you could do V squared versus L, or V versus square root of L. They end up giving you the same thing. The important thing for you is you need to know how to scale it properly. They give you a point, it looks like, for using most of the grid, plotting consistent with the quantities, and drawing a straight line. And then for E, using your straight line to determine an expression for G. If you do this, they're going to be off. So the value they gave was 8.1-ish for the slope that they found. So just be aware that you're going to be significantly off. Describe 2 ways in which the effects of air resistance could be reduced. So they're going to go ahead and basically assume that you had air resistance that prevented this from working. How could you reduce air resistance? Well, one way you could reduce it would be by doing it in a vacuum. That would be the obvious way to reduce it. The second way to reduce it, let's see, you could have a shorter rod. If you had a shorter rod, there'd be less surface area exposed. You could use denser rods so that it wouldn't be as subject to air resistance. You could use a more aerodynamically shaped rod. Lots of options there. All right. So I think that's it. If y'all have any questions, as always, feel free to ask, and go deer.